In the last few lectures, we had learned about numerical integration methods. In particular, we had learned about Newton-Cotes quadrature, which essentially means that you take adjacent points, maybe 1, 2 points or 3 or more, and send a collocation polynomial through them, approximating the integrand, and then replacing the integration, rather approximating the integration that you have to carry out by the integral of the polynomial. There are other methods that we also talked about, like Gauss quadrature, which as we have seen is more efficient, that is takes less number of function evaluations to carry out the calculation which is accurate to a much higher degree. And then we have talked about adaptive quadrature methods, which include things like the Gauss-Conrad quadrature. And in the previous lectures, we had also talked about how to implement these algorithms using the NumPy module. Today I am going to introduce to you a module, or rather a submodule. It's a new submodule. It's part of a new module called SciPy. When I say new, I mean it's new because we have not talked about this before. Not that it has been around only recently. And SciPy actually is a module for doing a lot of scientific calculations. It's built on top of NumPy. So it plays really, really well with NumPy arrays and provides a lot of different applications which you would want to use in real life. There are many submodules in SciPy, but the one which we are going to talk about, and one which is really perhaps the most important, is a SciPy.integrate submodule. And here I have for you a view of the documentation of which is available in the standard SciPy.org page, and which tells you roughly what this integrate submodule of SciPy gives you. It gives you various integration routines, something called quad, which we will describe in great detail. There are also double quad, triple quad, and other versions. Then there's trapz, trapz, Simps. These are names which should sort of invoke familiar algorithms. And this also says is that the integrate module also has integrators for ODEs, ordinary differential equations. We have not studied algorithms for handling ordinary differential equations yet, so we will defer the discussion on the ODE int part of this SciPy.integrate submodule till later. For the time being, we are going to focus primarily on the basic integration functions which the SciPy.integrate submodule provides. So, to illustrate how this works, when we start the Python interpreter, and as always, we start by invoking the standard mantra that we have. We don't even need the whole of the SciPy module for this lecture. We need to import the SciPy.integrate submodule, and I'm just going to integrate that as SI. Okay, this is not as standard convention as importing NumPy as NP is. The world over, everybody who uses NumPy in a big way usually imports NumPy as NP. So you will see this in many codes. I'm just using my own shorthand here. Instead of having to type SciPy.integrate all the time, and instead of taking the risk of dumping everything in the SciPy.integrate submodule onto my namespace, what I am doing is I am importing this with an abbreviated name of SI. SI of course for SciPy.integrate. Fine, so now we are ready with the imported modules. Now what does SciPy.integrate do for us? As I said, it can carry out various integration tasks. So let me illustrate a simple integration task. We had already seen how to use NumPy to carry these things out, but there we had to do a bit of computation, implement the algorithm, which was pretty easy to do in most cases, if you remember from the last few videos. However, we'll see that various functions in SciPy.integrate takes care of that nearly automatically. So let us say we want to integrate, let's say, the function x to the power 10, and from say 1 to 5. So what we can do is start out first with an array of x values, and we are going to use our old friend the linspace function to do that. I want to go from 1 to 5, and let's say I want 100 points. Right, so I've got my x values. And as we did for numerical integration using NumPy before, we need to find or need to create an array of the corresponding y values now. And since y is equal to 10, I don't really need to define a new function for this. It's straightforward. I just raise the array x's to the power 10, which, as you all know, means every element of the array x's is raised to the power 10. So now I started out with a 100 element array of x's, equally spaced values between 1 and 5, and now I have a 100 element array of y's, the corresponding values of the function x at 10. So how do I integrate this? Let's try a trapezoidal rule first, and for that SciPy.integrate, which remember we are calling SI, gives us a function trapz. That's a shorthand for trapezoidal. And for that, to use this, what we have to do is give it 2 arguments at least, y's to begin with. So remember, as the y values would go first, then you give the value of the x's, and you're getting something like this. Is this result accurate? Let's just check. The result really should be 5 to the power 11 minus 1 to the power 11, which of course is 1, divided by 11. And the answer is 4438920 as opposed to 4441577. Not too bad. At least we are getting 3 significant figures matching. So the result is actually within, it's out by 1 in 400 roughly. So it's accurate to within less than 1%. So not too bad, given the fact that the trapezoidal rule, of course, is bound to be exact only for linear functions, and x of 10 is really very far away from a straight line. The trapz, of course, uses trapezoidal, and now we have something else called Simps. And we are going to really describe Simps in some detail now, but first, the basic about how to use Simps, and the rule is essentially the same as when we use trapz, which is you supply Simps with a bare minimum of, actually it works with even 1 argument, but that's a bit tricky, so we'll come to that later. But it requires actually 2 arguments. One is the value of y's, the y values or the sample values of the function, and the value of the x coordinates at which those sample values were taken. So 2 arrays go in, the array y's, the array x's. By the way, these objects that we are providing as arguments to Simps has to be array-like. So this means that instead of giving actual arrays, we can give something which Python can internally convert to arrays. So things like lists, tuples will work. Of course, it's much more convenient to start with an array of x's and use the function to the raise to the power 10 on the array itself. So we will usually be using array arguments, but array-like arguments would also work. So let's see what this result is. It comes out as 4439014. So this is definitely an improvement over the trapz result. The trapz result was accurate to 3 significant figures. After all, the exact value to 3 significant figures is 444 followed by a string of values. The Simps result is actually accurate to 4 significant figures. So the accuracy of less than 1 part in 1000, which is quite good. Okay. Given the fact that you have to remember the Simps argument is actually supposed to be accurate for polynomials up to degree 2. Okay, let me just tell you one thing which I perhaps omitted to mention during the lectures on the Simpson integration method. It was designed to be accurate for polynomials up to degree 2, but if you are using in equally spaced intervals, which we usually do, which we are doing here, equally spaced in x I mean, then the algorithm actually turns out to be accurate for even cubic polynomials. This was only if you have equally spaced intervals and not unequally spaced intervals. Now hold on, you may, if you have been paying attention, you may have already spotted a problem here. We said while describing the Simpson algorithm, this of course is a composite Simpson algorithm with lots of intervals, not just 2 intervals as the Simpson algorithm originally is defined to be. In the Simpson algorithm, you need an even number of intervals. But in this case, when we have taken x's, what we have done is we have taken 100 points. What that means is that we have really 99 intervals. That's an odd number, of course. So how come Simpson's one-third rule, or the composite Simpson's one-third rule, is working in this case? After all, shouldn't it really complain that it doesn't have an even number of intervals to work with? Well, Simps actually takes care of that internally, and to understand what this is, we need to take a bit deeper look into Simps. So for that, let's again look at the documentation page, and here on the same page that we were looking before, under integrating using samples, it says trapz and Simps. So let's look at Simps. Okay, maybe I should increase the font a bit for this, so this will be visible. So it says quite a lot of stuff, but let's look at the basic stuff. SciPy.integrate Simps, of course, name of the function. Notice here all of this has 1, 2, 3, 4, 5 arguments, but all of them, apart from the very first one, have default values. What that means is that the only mandatory argument which Simps needs absolutely to work is the y values. Okay. But the order in which you have to give them is y, of course, comes in first. Then comes in x's, which have a default value, but as we have seen, we can supply the value of x's. Then we have other arguments like dx. Now, what is dx? Dx is nothing but a spacing between the x values. Now, you might be wondering why I have to give the spacing between x values. You have already given the x values. And you will be right in wondering that. The dx argument is used only if the x argument is not given. So, if you supply just say the value of y's, then Simps uses the dx argument. So, you can actually do this. You can say si.simps y's, and the result doesn't seem right at all. You are getting a much larger value than you had before. You already had a pretty large value. After all, this is of the order 5 to the power 10 or so, but this one is of course even a lot larger. Roughly 99 times larger, not roughly, exactly 99 Now why is that the case? The case really is, as I said, if you give only y, then dx is invoked and you have not given the value of dx, right? So the trouble is, if you do not supply the value of dx, Simps takes the default value, which is 1 as the spacing. So the x value spacing here is actually 1 over 99, not 1. But it is assuming that the spacing is 1. And remember, you have to multiply the final result by an h by 3. So it's the h in the Simpson 1/3 algorithm, which should really be 1 by 99 in this case, which is being taken to be 1. So what the correct answer would of course be this times the actual h value 1 by 99. Oops, I'm not getting it. The correct result isn't done. Oh, it's not 1 by 99 at all. After all, the spacing is 4 by 99. I missed that out completely. After all, 5 minus 1 by 99. And now that I've done this, I get exactly the same result, not the correct result, but the same result that the original Simps call with y's and x's thrown in was giving me. But you might be wondering, how do I give the dx values then? Well, can't I say 1 point by 99? And if I do that, I get an error. Why do I get an error? Well, you can see what it's saying. It's saying if given, you don't have to give it, if given, shape of x must be 1D or the same as y. So the problem is the order in which the arguments are to be given is y first, and definitely always, then x, then dx. So if I give it two arguments without mentioning anything else, Simps automatically assumes that the second argument I am giving is the x array. It's complaining that I have not given an array at all. I should have given a 1D array. What I have given actually is a number. Now how do I actually manage to give the dx value? That seems like a bit of a catch-22 situation. Dx will be needed only if x is not given, but if I don't give x and try to give dx, Simps apparently assumes that what I have given it is x. And of course, this is an error. Well, dx is a named argument, and then all of these arguments can be named. The first argument y, I don't have to name it because the first argument by default is always the y array. So I am using the y's array here. The second argument should have been x. Without using names, x would have been what Simps would expect. But as in all Python functions, you can actually name the arguments directly. Here I am saying dx equals, so it knows that this is dx value that I am giving. And again I made a mistake. I used 1 by 99 once again. Apparently I did not learn from last time. It's really 4 by 99. And I am getting back the same value that Simps was giving originally. So that sort of clears up, partly at least, the issue with x and dx. X is equal to minus 1. Minus 1, you should realize, always talks about the last element. So if you had a multi-dimensional array which you wanted to integrate, by default the integration will be over the last axis. Right now let's not worry about that, because for most of the time we will be integrating only one-dimensional arrays or one function at a time. This actually shows that you can actually integrate multiple functions at a time by using appropriate higher dimensional arrays. But as I said, let's not worry too much about that right now. What we really need to worry about is this other argument called even, and that we have already seen this in action so far. And remember the problem I raised? You have 99 intervals, which is an odd number, so how come Simpson's 1/3 rule is working? Now this is where the even argument comes in. It has a default value, AVG, which of course stands for average. And what is this? This is an optional argument. You don't have to give it. Of course, we did not give it. So argument can take three values: first, last, and average. And the nomenclature should make it pretty clear what it is doing. In this case, I have given Simps 99 intervals. If I had used even equal to first, then given the fact that I have given an odd number of intervals, the even argument comes into play. It would have taken the first 98 intervals if the value of the even argument were given as first, and then carried out the Simpson one-third rule using that even number of intervals. I could have given the argument last, which is take the last 98, or basically drop one interval either from the end if you are using the argument even as first, and if you give the value last for the even argument, it will take average. So last and first, just ways of making an even number of intervals out of a potentially odd number of intervals given. Of course, if you already have given an even number of intervals, then this particular argument has no effect. The default value is average, which essentially means Simps actually calculates the integral twice, once with the first n-1 intervals, in this case 98, again with the last n-1 intervals, that is 98 again, but the first 98 and the last 98, and averages the two results and returns back to me. So this is how Simps by default handles odd number of intervals given. Calculates for the first n-1, the last n-1, and then averages and returns the value to you. So this essentially is all about Simps, except for one thing. You might also be wondering, why do I need to give the excess array at all? If it's equally spaced, why not always give the dx array? Why even have the excess as an argument? The answer is we could, as I said, have used this for unevenly spaced samples as well. The dx argument works only when your x's are equally spaced, so you can say what is the gap between the x's. But if you have an unevenly spaced argument, a spaced independent variable, that is the x array is unevenly spaced, then Simps will actually take three successive points, send the parabola through them, and calculate the area under the parabola and keep on repeating that. And that theoretically is accurate only up to degree 2 polynomials and not degree 3 polynomials. So just let us illustrate that once. We will not be using unevenly spaced arrays a lot, except that sometimes, suppose you are trying to find out an area under the curve for an experimentally measured data, and you have not measured the experimental data with equal spacing for various reasons. Maybe it was very difficult to get equal spacing for the independent variable. In such cases, you have to use unevenly spaced data, and Newton coarse integration works perfectly well for that. In particular, the degree 2 Newton course, which is Simpson, works fine. Well, with a slight loss in the efficiency. So, just to illustrate that, let's now kick up another array which is not evenly spaced, and I will take a small array because I will write it by hand, so I will not take a 100 element array. Let's say 0, 0.9, 1.3, 2.0. So that's a 4 element array. And what I want to do is show you that for a cubic function, so let's just take there are 3. Simps actually gives you a close result but not an exact result. So it's y's and x's. This is all you have to give. Of course, the result should be 8 minus 0 by 3, so 8 by 3. as an integral. Remember, you are integrating from 0, that's the left hand, to 2, that's the right hand. You are integrating, you are integrating x of 3, so the answer should really be x of 4, 16 by 4, 4. That's the exact value. What I am getting is 4.194. Not really exact, but well, not too bad either, given that we are using only 4 points. But even if we had used 4 points, but equally spaced, so let's try it again. And not instead of array, let's use linspace now. 1, 2, 4. Sorry, not 1, 2, 4, 0, 2, 4. So 4 equally spaced points between 0 and 2. Of course, that means 3 intervals. Odd number of intervals, so even in the last evaluation, since it was actually calculating the average of the first 2 and the last 2. Let's try SciPy.Simps. Okay, after I calculate the y's now. So these are equally spaced, yet I am not getting an exact result. I am in a bit of a pickle over this, but the one case when okay, let's try 3 intervals, 3 points, 2 intervals, and with this I get the exact result. So yeah, I get an exact result provided I am using an even number of intervals. So averaging, that is usually a good thing, actually turned out to be a bad thing last time. So with only 3 points, equally spaced points, I am getting an exact result for even a cubic function. But for unequally spaced points, I will not get an exact result for a cubic function. But remember that's so let's go back to the original array once again, and this time let's try it for a quadratic function. And x square of course integrates to x cubed by 3, and from between limits 0 and 2 you get 8 by 3 as the integral. And let's see what Simps gives us. So not the exact result again. It's supposed to, but doesn't. But that again is the result of the fact that we are using an odd number of intervals. Let's say, let's just repeat with an even number of intervals. Just 3, less points than before. But, and now try Simps. I get 2.6666, which is actually exactly 8 by 3. So, remember, averaging may be good, but sometimes it may mess up the thing. Okay? So this is all I had to say about the Simps integrate function. We have the Simps function from the SciPy.integrate module. In the next lecture, we will describe the quad method and briefly touch upon the other integration routines like double quad, triple quad. That is for 2-dimensional and 3-dimensional integrals and so on. So, before you listen to the next video on quad, I would urge you to review the videos that I had earlier on Gauss quadrature and Gauss-Grondot quadrature. That is adaptive Gauss quadrature, because that's really what quad does behind the scenes. So, until the next video then, bye for now.